kind of describe them. And then when you can see them in person, it'll be a little bit better. One of the first ones I do is to, I have an aluminum pipe, and I mentioned this yesterday, that pretty good sized actually. And actually one of the guys at LIGO gave it to me one time. They were up on kind of a touring science show and had a bunch of demonstrations. And afterwards, I was so impressed by this aluminum pipe. I've done it with copper pipes, but it was kind of more impressive with the aluminum one. Anyway, you drop a magnet down it, but here's the first thing. An aluminum pipe. And let's see, I'll draw another little thing here. And that is, I have some disc magnets stuck to the board. And it's a neodymium or neodymium magnet. And these things are pretty impressive. You can get a very strong magnetic field for a particular weight of magnet or particular size of magnet. The one disadvantage they have is that they're very brittle. And so if you drop one on the floor, it'll break into pieces. And I have quite a few of them that are partial magnets because they've been dropped. Anyway, you take this thing and you try to stick it to the aluminum pipe, and it won't stick to the aluminum pipe at all. And you take another piece of aluminum and stick it near this thing, no reaction at all. Aluminum is not magnetic, doesn't respond to it, but it is a conductor. So you take this neodymium magnet and drop it down the pipe. Now you can preface this by dropping something else down the pipe, like a marble or a washer or something like that. So you drop the aluminum pipe down, or a neodymium magnet down the aluminum pipe, and then you can look down the pipe while it's falling, and you'll see this thing just working its way downward slowly, kind of twisting and flipping sometimes, but at any rate, it's going very slow through the pipe, and then finally it'll drop out of the bottom of the pipe. And you can do it again and again and again, and it's just kind of amazing seeing that. So something's going on with that, and it'll never actually move over to the side of the pipe and stick or anything like that. It's just as if it's falling through a thick syrup or something. So that's kind of an interesting experiment. Another one we have is that we have this is just a pendulum support actually is all it is. It's a rod that sticks out of something, a stand or whatever. And we have these little pendulums that kind of hook onto this thing. And there are various shapes. And one of them kind of looks like a fork, actually. It's got a whole bunch of narrow tines on it. And try to come over here. Anyway, that aren't connected down at the bottom. So it's just like a really weird fork or something like that. And you can swing it back and forth on the pendulum, and it just goes back and forth for a while. In fact, any of the different attachments that we use, and I'll kind of sketch what they look like. We have one that's, whoops, they are symmetric, no matter how I draw them. So there's one that kind of looks like that, and it's got some holes in it. And so I don't know how many like that. And this one, if you put it on the pendulum support and swing it back and forth, it'll swing for a long time too. We've also got one that is just a solid paddle, although it's thin. And all of these are made out of aluminum. So They're all aluminum paddles, but they're of these different shapes. And then I've got this little magnet stand that I can set up. And here's the way it looks. It's actually got kind of a face that comes up like this. It's got a rectangular base that it sits on, so it can be pretty sturdy, and it's symmetric despite how I might draw it. And at the end of it, and this thing's made out of like steel or something like that, but at the end of it, it's got a pair of neodymium magnets or neodymium magnets. I've seen it pronounced both ways or heard it. So okay, so you take this thing and bring it up to the pendulum support so that looking down the flat plane of the pendulums, they're going to be swinging between these things. And again, before I do this experiment, I demonstrate that magnets do not stick to aluminum. And so you'd think it wouldn't have any effect on there. But when I've got this thing at the bottom point of the pendulum, then I'll bring one of the aluminum things up here. And actually, I usually do it with this one first, the solid aluminum paddle, or the one that doesn't have any holes or tines on it like a fork. And I bring it up to the side, let go and let it swing down between here, and it stops like that. It's like it ran into a brick wall, except you don't hear any clanging sound. It just, as soon as part of it starts to get between those neodymium magnets, it starts to slow down and it'll be stopped by the time it reaches the vertical position. Now, you can repeat that with the one that has the holes in it, and it doesn't stop quite as fast, but it'll come to a stop pretty quickly. Do this one that has the tines on it that are not connected at the bottom, and it'll swing back and forth a little bit, maybe get a few swings in before it comes to a stop. They all come to a stop much quicker than they would if there was no magnet there, but this one will swing for a little while. So what in the world is going on here with these things where this magnet drop through here falls at a snail's pace? These moving things experience some sort of a braking effect, and they're brought to a halt almost immediately. In fact, it's something that, well, I don't know if you probably wouldn't have an aluminum saw blade, but you can imagine a magnetic brake for an aluminum wheel that could bring it to a stop fairly quickly without any contact between it. And so you wouldn't have any friction acting. Okay, well, people were studying things like this back in the 1800s, and one of the things that they arrived at was that a changing magnetic field will produce an electric field. Okay, our dog's outside and I'm not going to bring it in today so it doesn't snore on the floor while I'm trying to teach. Anyway, that's the way that it can be produced. And what we're seeing in every case is that effect, but it's not, that doesn't go all the way toward explaining this thing. Turns out if you repeated all these words and just switched two of them, changing electric field will produce a magnetic field that happens to be true as well. And between the two of these things, that's how electromagnetic radiation manages to travel through empty space, through a vacuum. You have a magnetic field that's oscillating in some time with some frequency, and it will produce an electric field that also oscillates with the same frequency. Now, weird things about this, if you have a magnetic field that's changing, maybe this is the magnetic field going up and down in that direction where it's increasing to some value and then changing or decreasing back to zero and changing to some value, you'll get an electric field that is at right angles to it. And that'll also be changing in time, exactly the same frequency. And the velocity of the electromagnetic wave ends up being perpendicular to the two of those things. These two, the electric and magnetic fields, will determine a plane. The direction they travel is perpendicular to that plane. And I may not have gotten the direction of the velocity quite right. It might be in the opposite direction. There are rules for this, but that's what, well, actually, it depends on time. But anyway, that's how electromagnetic waves happen. But we're just going to be concentrating on this first one, that a changing magnetic field will produce an electric field. And we won't try to get all the way to the end of the mathematics of this today, but we're going to be studying this for the next few days. But let's try to understand what's going on with these things. Okay, the swinging paddle. If it swings down into a region where there's a magnetic field, so here's the paddle that is swinging down here, and here's a region where there's a magnetic field, and let's just imagine that it's into the page here. There's B, and that's just between the magnets that you've got on the thing here. Well, what's going to happen is, in the space of that aluminum paddle, as it's swinging into this, it will be experiencing a changing magnetic field. And so just because of its motion, okay, well, that changing magnetic field that it's experiencing will produce an electric field in the aluminum paddle. And what do electric fields do? They make charges move. And so now you'll have a current inside this aluminum paddle, an electric current. And what do magnetic fields do to electric currents? They exert a force on them. And that's what slows down the paddle. Same thing happens in this case, except in this case, it's the magnet that's moving. And if you imagine, I'll kind of draw the magnet inside here. Here's our little disc that's falling through here. It'll have a magnetic field that's shaped like a dipole. And so the magnetic field of this disc will be something like this. And I'm not the greatest at drawing these things, but I only drew a few magnetic field lines. But as this thing falls, the parts of the aluminum pipe will be experiencing a changing magnetic field. And that changing magnetic field will produce an electric field in the aluminum pipe, and you'll actually get currents in the aluminum pipe that travel around. And in this case, let's see, it would go in the opposite direction at first. And so the electric field will be like that, and that'll make a current flow in there. The magnetic field will exert a force on the current, and the current exerts a force back on the magnet. That's kind of a Newton's third law thing there. And that's what slows down the magnet. So just kind of crazy. Now, what's going on with this thing is that the nice solid paddle has room for larger currents that can be produced in it. And so it gets stopped faster. The one that has holes in it, the currents are limited to just particular regions. And so you can't have as big of current loops in there. You might have things like this, or maybe things like this a little bit. This one that just has the tines, the currents are limited to being only as wide as the tines happen to be, and they're actually pretty narrow. And so this doesn't have very big currents. They don't get acted on very well by the magnet. And so this one doesn't get stopped as well. This one gets stopped really well. It's just brought to a halt almost instantly when you see it. And it's just kind of amazing to watch that thing. So all of these are based on this idea. Now, we are going to get a bit more mathematical about it. But first, I wanted to talk about something else that one of the homework questions has to do with a plane flying over Antarctica and discussing that there's a magnetic field in Antarctica that points in a particular direction. And this has to do with something called motional EMF. And EMF is something that stands for electromotive force. Some of the language that's used here is sometimes a little bit archaic and confusing, and we tend to not use the unabbreviated version. We just call it an EMF, but it's like a potential difference, except it's a weird kind of potential difference sometimes. But anyway, for starters, we'll just imagine that we have a conducting bar here, and this could be an aluminum bar. It doesn't matter as long as it's conducting. And copper could be iron, could be steel, could be stuff that has some magnetic properties of its own, but it doesn't have to. All it has to be is a conductor. So conducting bar of some sort. And then let's imagine that it's going through a region of space where there's a magnetic field that points down. And so, maybe it's like it's flying in the Earth's magnetic field or something like that. So it's heading in this direction, and this is the velocity of the bar. Well, if it's a conductor, it's got charges inside of it that are free to move. And so usually they're free to move in the presence of an electric field. So if you hooked it up to a battery, you'd have a current flowing around there through the bar. But in this case, we're not going to have a battery. In fact, we're going to make this into a battery. And here's the deal. If you imagine a positive charge in this thing, maybe, and actually we know it's the negative charges going in the opposite direction, but QV would be in this direction, B is down, there'd be a magnetic force on a charge in here, and that force would have a magnitude of, we'll just call this F here. F is going to be QV cross B. Now, if it's a negative charge, it would get pushed down in this direction. And we know it's actually the negative charges that are free to move in a conductor. So what you'll end up with is a bunch of negative charges building up on this end of the bar and leaving behind positive ions up on this end of the bar. So it's as if you had positive charge that migrated from here up to here, but it's actually the negative charges go in the opposite direction. Well, if you've got an imbalance of charge here and you get positive here and negative here, you're going to have an electric field in this thing that's produced by this motion through the magnetic field. And there will actually be an EMF, or a potential difference between the two ends of the rod. And if we think about it, let's see, it was pushing Well, they keep moving until the electric field balances the magnetic field. And eventually, the net force that's on the charges will equal their charge times an electric field plus their charge times V cross B. And let's see, you can divide out the charges, but that'll end up equaling 0 after a while. You'll get a kind of equilibrium situation. And what you can get out of this is that the electric field will equal the negative of actually QE when you reach that equilibrium situation. And you can divide the Q's out and you get that E is going to be in the negative direction of V cross B. Well, V cross B is going to be in that direction. So the electric field here is going to be pointing downward in this. And so, and you'll get a potential difference between the two ends of the bar that's moving through this magnetic field. And the potential difference will actually equal the negative of the integral of E dot dl. Well, if you start up at the top and have your E dl integral going in this direction, you'd get a positive thing, but the potential difference is the negative of that. That'd be the potential at the bottom minus the potential at the top. So if you take the bottom potential minus the top potential energy, you'll actually just get E times L or minus E times L. But that will, you got a negative because well, you took the negative of the integral is what you did. The integral itself was positive, but it turns out that this potential is going to be lower than that potential. So the higher potential is the positive end, the lower one is the negative end. And we call this potential difference the EL, or just the magnitude of that EL. We use kind of a scripty E for that, and it's the EMF. That's the symbol we use for an EMF. Sometimes we use that for the potential difference that a battery will provide, but that's the induced EMF in this case. But since the EL was equal to QVB, turns out that induced EMF there is just going to equal QVB in this case. V was perpendicular to B, and we're talking just magnitudes here, so we'll get that. So the induced EMF will equal QVB. And so we've got all those nice little things there. Oops, I had to, no, I divided that out, hadn't I? And I also forgot the L. I had to multiply the E by the L, so VBL. So the longer your conductor happens to be, let's try that again. And this is just magnitudes on these things. The longer the conductor is, the greater the potential difference you can get between the ends of the thing. There was an experiment done, let's see. Wow, it was probably still when they were launching space shuttles. So it would have been prior to about 2011 or so. But I think it was more like around 2000. But they had a space shuttle mission and they dangled a long wire out the end of it. And the space shuttle is going around the Earth, but it's still within the Earth's magnetic field. In fact, the Earth's magnetic field isn't that much weaker up there, but it had a really good speed. something like 17,000 miles an hour, and they dropped a long wire out of the thing just to see how much of an EMF it would produce. And I can't remember exactly what the finding was in that case, but it would have been kind of a fun experiment to do. But anyway, this is one of the homework problems. It's actually a question, homework question. It's about flying an airplane over Antarctica, and they give you the direction of the magnetic field over Antarctica. And let's see, you're to assume that the wings of the airplane are conducting. I can't remember if I actually stated in the problem that they're conducting, but that's something that's happening there. Okay, well, I want to get to one of the laws that we're going to have here. And this is called Faraday's law. And I think some of you might have, whoops, D-A-Y apostrophe S. Some of you might have written about a biography of Faraday. For somebody who didn't have any formal education, he's got a pretty cool law that's named after him. And it ends up being this, that if you have a closed loop, and the closed loop can be in space, it doesn't have to be within a conductor or anything else, there will be an EMF in this closed loop, which we'll kind of just write as a scripty E like that. And this will actually equal the integral around your closed loop of E dot dl. So anyway, this will be talking about this induced electric field, but it ends up equaling this. It'll be the negative of the time derivative of the flux of the magnetic field through that loop. Holy cow, this is kind of weird. So you just imagine a loop in space, and I'll draw something round for a change. But I'm going to draw it as something that's kind of discontinuous, actually. And I hope I keep picking the same hole every time. I don't remember which hole I was using. Anyways, so there's our Faradayan loop or something like that. And let's suppose this is in a part of space where at some instant, maybe we've got a magnetic field that's pointing into the page. Okay. So within this area, there's going to be some magnetic flux going through that thing. And so we can talk a little bit about that. And that, let's suppose that the magnetic field actually has some time dependence. So it's not constant, it's changing in time. And we could have all sorts of different expressions for how that might be changing in time. But at any rate, it's changing in time. And if we calculated the magnetic flux through this thing, and let's just imagine that this thing has an area of A, and that the flux of B through that thing, it'd be into the page, would just equal B of T times A. And so that's what flux is. It's like when we were doing this with electricity, we talked about the flux of an electric field through some surface. And sometimes we had flat squares, sometimes we had other things, but it'll just be B or E times A in that case, or more generally, the flux of the electric field through some area. We'll imagine that we have a constant electric field. It would be like E dot A, would be the flux of A. Well, magnetic field is the same way. The flux of the magnetic field through a surface, and the vector A is chosen to be perpendicular to the surface, so we're going to restrict ourselves to plane surfaces, so that circle would all lie in the plane of the piece of paper, but it'll end up equaling just B dot A. So that's equal to BA and the cosine of phi, where phi is the angle between B and A. But if you happen to have B and A being perpendicular, cosine of 0 is 1, and so that's where you get the maximum. And that's kind of the situation I've imagined here. But if we have a time-changing magnetic field here, I can take a derivative of that, and I'm going to stick a minus sign on the derivative, and I'll talk about that in a second or a few minutes. But d flux of B dt would end up being the negative of the time derivative of B of t times A. And actually, I assumed for this problem that they were the B was perpendicular to the area, the plane of the area A. Well, A is constant in this case, although we will do some problems where it may be A that's varying and not the magnetic field that's varying. So that could be interesting. But that'll produce this induced EMF. Okay, and this will end up having units of volts or joules per coulomb. Although it's not going to be easy to show this. Actually, maybe we could. B has units of Tesla, and so we'd have Tesla meters squared for the units of this part. But if we take a time derivative, we're actually dividing by units of seconds down there on the bottom. Let's see. Well, remember what a Tesla was? It was a Newton per amp meter. So we would have a Newton per amp meter, and then I've got meters squared over seconds here. And let's see, that'll divide with one of those, and that'll be that. And so this will be a Newton meter on top, but that's a joule. So we would have a joule. On the bottom, I've got an amp second, but an amp is a coulomb per second, and I'm multiplying that by seconds, and I end up with joules per coulomb or volts. So that's how this weird thing can give us units of volts. Okay, so that's just one of the ways this thing can manifest itself, and we would call this the induced EMF. Now, it's a weird induced EMF because what it's going to be produced by is an electric field that, in this case, when you're going around this circle like this, okay, it's an electric field that exists everywhere in this loop that's just in space. It doesn't have to have a conductor there. And the thing is, if you go around this loop once, with something like a circuit, if you go all the way around the circuit, you get back to 0. You'll actually have a bunch of voltage rises and voltage drops in a circle. This just keeps increasing. So if you go around this loop once, you'll get 1, or E times 2 pi r. If you go around it again, you'll get another E times 2 pi r. Where that would matter is if you have a coil that's in here, and each part of the coil would have an induced EMF in there, and you can induce currents in there. In fact, that's another demonstration I'll show you, is we'll take one coil and have current go through it, and then we'll bring another coil inside of it and see there's no electrical contact between the two, but we'll see that there's a current induced in the second coil because of the other one changing. So this is all kind of weird stuff, but let's try one problem and maybe a couple of problems and see how we can make this work. Okay, so this would be a pretty early problem in chapter 29. Yeah, chapter problem 8 anyway. We have a flat circular steel loop of radius 75 centimeters. Okay, so that's this thing here. Is at rest in a uniform magnetic field as shown in the edge-on sketch below. So the magnetic field points in this direction. So there's an angle between B and A. A is always a vector that's perpendicular to the plane of the area that we're talking about. So here is our A vector looking like that. And if I slide it over here, there's an A vector there. I can see that there will be a 30-degree angle between A and B. Okay, so at any given time, the flux of the magnetic field will equal A dot B, and that's going to be A times B times the cosine of 30 degrees. And I don't know, let's see. I don't know how many significant figures we've got to work with on this thing, although they do put 2 sig figs on these. So I'll just go with 2 sig figs on what we're doing here. And this is a circular loop. So it says find the EMF induced in the loop as a function of time. Okay, well, the EMF, the script E is going to be, at least in magnitude, it'll be the deflux of B dt. And take a time derivative of this. The area is not changing, but the magnitude of B is. And so I'll actually get d by dt of AB cosine of 30. And it'll end up equaling A cos 30 dB dt. Now the area of this thing is actually going to equal, we'll be able to put a number on this. Radius 75 centimeters. So it'll be pi times 0.75 meters squared. That's just pi r squared. So that's what it happens to be. And let's calculate dB dt while we're at it. Got a complicated expression. It'll be d by dt of, let's see, 1.4 Tesla times e to the minus 0.057 seconds to the minus 1 times t. So that's what I'll be taking a time derivative of. And the 1.4 Tesla can come outside the derivative. And when you take a derivative of something like this, d by dx of e to the alpha x ends up giving you alpha e to the alpha x. You just kind of get the same thing back again. So we'll end up with the derivative. I pulled down the constant, negative 0.057 seconds to the minus 1. And then I'll still have the e to the minus t stuff at the tail end of that. So let's see, calculator time, I think. It will end up being dB dt will equal minus 7, actually it's minus 8.0 times 10 to the minus 2. And then units on here, a Tesla, I'll just call it Teslas per second. And then it's still got the exponential out there, e to the minus 0.057 seconds to the minus 1 times t. So that'll be dB dt as a function of time. Yeah, and if I just multiply that by the area and the cosine of 30, I'd get the flux as a function of time. So pi times 0.75 x squared. This is 1.77 meters squared. So I guess I can just go on with this one. That's a blank sheet of paper. The flux of B as a function of T. Oh, this is d by dt. Oh, the flux of B was that. That was part A. No, it wasn't. Part A is finding the EMF induced in the loop as a function of time, which is this thing. So I have to take d by dt of that, and we had that. It'll be A cos 30 times the dB dt, and we've got everything figured out at this point. So it would be 1.77 meters squared. That's for the A, times the cosine of 30 times minus 8.0 times 10 to the minus 2 Tesla per second times e to the minus 0.057 seconds to the minus 1 times t. Good, it all fit. And so we can get an expression there for all that. So, well, what am I in? I'm in degrees, good. And I get 0.12, and this would be Tesla meters squared per second. And I think that ended up being volts. So, and I'll write that out, volts, and then that's times e to the minus 0.057 seconds to the minus 1 times t. So that would be the induced EMF as a function of time. Says, when is the induced EMF equal to 1/10 its initial value? Well, the initial value is what you'd have at time 0. If you put a 0 up here, e to the 0 is 1. So the initial value is 0.12. It'll be at 1/10 of its initial value when this is equal to 1/10. So we could just say that e to the minus 0.057 seconds to the minus 1 times t is going to equal 0.1. And we want to know, when is that the case? Well, if you take a natural log of both sides, natural log of e to the something is just that something. So is just equal to minus 0.057 seconds to the minus 1 times t, which is equal to the natural log of 0.1, or t is just going to equal, and the minus sign I'm not too worried about on here, but it won't actually be a negative time. Oh, this thing will end up being negative is what it is. And that will equal it would take 40 seconds for it to drop to 1/10 of its initial value. Okay, then it says, find the direction of the current induced in the loop as viewed from above the loop. Okay, now this is something that you can try to get out of the mathematics, but it's easier to understand it through something called Lenz's law. And I think there's a pretty nice, concise statement of it in your book. Experiments. Okay, I don't know if you can read this or not. Maybe not. But it says the direction of any magnetic induction effect is such as to oppose the cause of the effect. All right. Well, in this case, what we have, if we look down from above, we're looking at this circular steel loop. Okay, so this is our flat circular steel loop, or maybe we could imagine it as being like a thin washer or something, but it'll look like this. And it does have a magnetic field that's coming out of the board. We're going to be looking at it from above here because it says as viewed from above the loop. Yeah, so there's a magnetic field that is coming out of here. It doesn't come straight out, it's going at an angle, but the magnetic field is becoming smaller in magnitude as time goes on. That's what that decaying exponential on there is. The B of T, the strength is 1.4 Tesla times e to the minus 0.057 seconds to the minus 1 times T. That's a decaying exponential. That's the thing that you saw when you graphed the charge or the current through the capacitor as a function of time. That was a decaying exponential. So these X's coming out of the page are going to get weaker with time. That means the magnetic field through this thing that's coming out of the page is going to diminish in time. Well, the effect of the induced EMF is to oppose that change. Well, how can it do that? How can it keep that magnetic field from reducing in time? It can happen by making the electric field point in this direction. The EMF would cause positive charge to circulate. Actually, it's negative charge going the opposite direction, but the induced EMF will be in a direction to produce a current going in this direction that will produce a magnetic field coming out of the page that will oppose the reduction in the original magnetic field. So that's kind of hard to wrap your head around, but as viewed from above, the current would be in a counterclockwise direction in this case. So kind of hard to quite wrap around your head around some of these things. Let's try another problem. If we do enough of these things and you keep thinking of them through some of these relatively simple terms, something to oppose the effect that produced it, eventually it may sink in. Anyway, we'll start off a square copper loop, 10 centimeters on a side. Okay, that's not too easy or too hard to draw. So this is 10.0 centimeters on a side. All the dimensions are that. So Located in a region of changing magnetic field. The direction of the magnetic field makes an angle of 37 degrees with the plane of the loop. Oh, well, that's a bummer. So we'll have to do something that try to deal with that. The direction of the anyway, the time-changing field has the following time dependence. This is almost just like the last problem. B of t equals 0.10 t plus 1 times 10 to the minus third Tesla per second times t, except this is a magnetic field that's going to be increasing in time. Okay, because if you graph the magnetic field as a function of time for this thing, at time 0, it's 0.10 Tesla, and it just keeps increasing, at least as long as it takes us to solve the problem, we could say that. And so this is B as a function of t. All right. So induced EMF in the copper loop for times t greater than 0. All right. Well, the induced EMF is going to equal B dot A. That's the magnetic flux, but we have to take the time derivative of that. Okay, and I probably should have started this off by doing the induced EMF is going to equal the time derivative of the flux of the magnetic field with a minus sign on there. Okay, so we don't know, well, yeah, it just says it makes an angle of 37 degrees with the plane of the loop. We don't know if the magnetic field's going up or down, making that angle of 37. But if we look at it edge on, we could imagine the area of the loop is pointing this way, and we'll just make a choice. And if we don't like that choice, we could just flip the situation upside down and think of that as the positive direction. So this thing makes an angle of 37 degrees with the plane of the loop, which will make this thing 53 degrees, I think. Something like that, the angle between A and B. Okay, so the induced EMF will equal magnitude of B, the time derivative of the magnitude of B, magnitude of A, and the cosine of the angle between them, cosine of 53 degrees. Is this what you get on a 3, 4, 5 triangle? I bet that's why they picked it, maybe. Yeah, it is. So the cosine of this angle is just 0.6. And it's a square rectangular loop. So we will just have A, this is 0.10 meters times 0.10 meters, 100 meters. That would be 1 times 10 to the, or 10 times 10 to the minus 2, 10 times 10 to, that would be 100 times 10 to the minus 4, which is 1.0 times 10 to the minus 2 is A. So meters squared. Cosine of 53 is just 0.6. Check it out on your calculator. And then dB dt is all we have. Well, B is that if we take dB dt, the time derivative of this is 0. The only thing we get out of this is the slope of the graph, which is 1 times 10 to the minus third Tesla per second. So I can just plug this in and I'll have 1.0 times 10 to the minus fourth meters squared times 0.6. Cosines are dimensionless, and you could call it 0.60 if you want to. Although, yeah, we have at least 2 sig figs, but we've only got, yeah, we only have 2 on the angle, so that's why. And dB dt is just going to be 1.00 times 10 to the minus third Tesla per second. And somewhere along the line, I lost my minus sign. So reintroduce it there. Oh, you can do this in your head. 1 times 10 to the minus fourth times 6 times 10 to the minus 1 is 6 times 10 to the minus fifth times 1 times 10 to the minus third would be 6 times 10 to the minus eighth with a minus sign. And it'll be volts. But I'm going to check that because I was doing that pretty quick and I may have made a mistake. Yeah, 6 times 10 to the minus 6.0 times 10 to the minus eighth. And it'd be Tesla meter squared per second, which is a volt. Okay, and that's a constant induced EMF. This just because of the way this thing is changing in time. It's got a constant change in time there. Okay, now if we were looking down from above on this square copper loop, what we would have is a magnetic field through it coming out of the page here that's increasing steadily. The EMF would be in a direction to oppose that change. And so if the EMF is in this direction, you'll have a current flowing in this direction, and it will produce its own magnetic field going in the opposite direction of this one that's increasing. And so there's something that we have there. Okay, so there are some introductory problems on induced EMFs, and we'll do some more coming next week. And then Tuesday, I want to show you as many demonstrations as I can set up and show you in an hour or so. So that's what we have for today. On to a new area. And this will be our last chapter in the magnetism section. I put in the syllabus or maybe put on Canvas that maybe we would get to chapter 30, but I don't think that's going to happen. So when I took this class at Eastern, it was actually spread over 5 quarters. And we had the time in those 5 quarters to get a lot of these. They've now trimmed it back down to 3 quarters. So we spent a lot of time fall quarter, just some of it, we actually did some epsilon delta proofs in the physics class, first quarter of the physics class, but we don't do that anymore. So. Okay, are your minds befuddled by what was going on today? I'll stop the recording and I'll see all 3 of you tomorrow morning. Be aware the weather forecast is for